Hi there, Mr. Sutton here, bringing you the Algebra 2 4-9 lesson on modeling with polynomial functions. In this one, we will be writing equations of polynomials given some x-intercepts and another point, and we'll also be doing some polynomial regression. For our first example, we're going to go through how to write a polynomial function, a cubic function specifically, that goes through certain points. Now, the way these problems are set up, there's going to be a bunch of x-intercepts that we know about, and there's going to be one non-x-intercept point that they also need to give us for us to really give an accurate equation. So to start this off, we're going to write an x minus p factor for each of our x-intercepts, so x minus whatever the x value is, and then we're also going to put an a out in front. Pause the video and see if you can come up with this kind of initial equation. Alright, so going from left to right, we're going to have x minus negative 4, which is really x plus 4, and I'll put my a out in front of that first factor. And then we've got a 1 over here, so x minus 1, and then finally x minus 3. Now once you've got all of this, this isn't quite enough to get the full description of the polynomial. We need to figure out this a value. So the way we're going to do that, they gave us another point that was not an x-intercept, this 0, negative 6 point. So whatever that other point is, and it doesn't have to be a y-intercept, it just happens to be in this case, whatever that other point is, you're going to substitute that non-x-intercept point for the x and the y, and that will let you solve for the a value. So pause the video again, see if you can do that to figure out a, and then when you find a, just substitute it back in to get the full equation. Alright, so we're replacing this f of x with negative 6, and all of these x's in here with zeros. So we have negative 6 equals a times 0 plus 4, 0 minus 1, and 0 minus 3. So this is going to be 4 times negative 1, which is negative 4. Negative 4 times negative 3 is giving us 12. So this is 12a equals negative 6. And then if I divide both sides by 12, we end up with negative 6 over 12, which we can reduce to negative 1/2. So that's our a value. Don't forget to actually plug this back in to get the formula. So we have f of x equals negative 1/2, x plus 4, x minus 1, x plus 3. We're going to do one more of these problems, trying to write a polynomial given a set of points. This time around there's just no graph. Other than that, pretty much the same idea. Pause the video and give this one a shot. Alright, so first we're writing our kind of general equation with the a out in front. So my first 0 going left to right, we've got negative 4. That's negative 4 comma 0. So we're going to have a parentheses x plus 4. And then let's see, this next one is, it has a 0 in it, but this is actually a y-intercept, not an x-intercept, because the x value is 0 and the y value is something else. So we'll use this one later on. This next one here, we've got x minus 2, and then finally x minus 5. So now we'll use this 0, 10 point to get our a value. So I'm plugging 10 in for f of x, or y if you like, and then 0 is going in for all these x's. So we have 4 times, this is basically times 10 here, so that's 40a. And then dividing by 40, we get 1 over 4 if we reduce that. Plugging that back in, we have f of x equals 1/4, x plus 4, x minus 2, x minus 5. On this next one, we are given a table of values, and we're not going to try to write a polynomial for this one by hand. We don't even have any x-intercepts or anything like that. What we're going to do is use Desmos technology to find a function that fits this data, and I'm actually going to call this polynomial regression. There we go. Because it is writing a polynomial, but it's a more specific method. So the way to get started on this, you're going to want to copy this table into Desmos, and then once you've done that, you can use the zoom fit button if you like, but at the end of the day, you need to at least try a cubic regression. I mean, you can try quadratic or whatever, but eventually you're going to try cubic to see if that gives you an r squared value of 1, if it gives you a good fit. And you can check this both numerically and visually. On the off chance that r squared does not equal 1, you can always try a quartic regression to get a better fit. And you can't do any higher than a quartic regression in Desmos, but that's usually more than enough for these. So pause the video and see if you can make that happen. All right, let's go to Desmos. So here we are. And just in case you forgot, this little plus button up here is how we can add tables to Desmos. And for the x values, we've got 1, 2, 3. We're going by ones. So I'm going to write 1, enter 2. And after you've done the first two for the x values, it's going to assume you want to use the same distance between them. So it's automatically going to give me 3, 4, and 5 just by pressing enter, which is kind of neat. But if you don't want that, you can always change them anyway. Now for the y values, we've got 1, 4, 10, 20, 35, 56, and 84. And while I'm doing these, Desmos is faithfully entering them onto the screen here. So what I'm going to do is, well, I already did a zoom fit earlier on this thing, but if I weren't all zoom fitted, I could press this little plus magnifier button and get a nice window on that. The more important piece of this, though, is going to be this button up here that does our regressions. Now, we've done linear and quadratic regressions before. This is the same idea, same button, only this time in the drop-down menu, you'll notice that below quadratic regression, we have a cubic regression, which I'm going to do. And I'm going to take a look at my r² value. That tells me how close of a fit it is. If this is 1 or pretty close to 1, then it matches our data pretty well. If not, then you might want to try a different regression. This one was a perfect match, so we're going to just keep that. But if it didn't work, you could always do a quartic regression. For our purposes, though, we want to take the simplest regression possible because simpler is better when you're dealing with algebra. So here was the graph that we came up with, and here was the function on there. I'll show it to you one more time. So let me go back here, and it was this. This is actually like 1 over 6, although it's hard to tell with the decimal. So we have 1 over 6 x cubed plus 1/2 x squared plus 1/3 x plus 0, which we don't really need to write. So there is our formula for this one. For our last problem today, we're going to end with a more patriotic final boss battle. Say hello to our friend the bald eagle here. We've got some data in a table showing number of bald eagle nests that were counted in Ohio 10 years after 2000. I kind of wonder if this actually is a real table or if they just kind of made this up. But hey, let's go with it. So they want us to find a model for the data and then use it to estimate the number of bald eagle nests in 2015. And this is really why we're making these models. We don't just make them just for the fun of it. We might actually want to be able to get more specific values that are not explicitly in this table. 15 is kind of covered by the table values almost, but not quite. It's like between 14 and 17 here. So we would probably expect it to be somewhere between 200 and 221, but who knows? So this is the same idea we did when we did just a regular regression before. Pause the video, use whatever regression you think works best for this, and then see if you can use the function you generate to figure out 2015. All right, let's go to Desmos. And this time my table is going to be a little bit larger than last time. We're not quite going by ones. We do for a while though. So we've got 0, 1, and then 3, 4, 5, 6, there we go, 7, 8, 9, and then this next one is not 10, it's actually 12, 14, and 17. So we have to off-road a little bit with those x values. And now for the corresponding y values, we had 63, 73, 79, 88, 108, 125, 150, 164, 184, 215, 213, they went down that year, 200 down again, but then they bounced back up to 221. So let me just get a nice little zoom fit window just to see what these bald eagles are doing. There we go. And then let me try out a regression on this. So there's your linear regression. That doesn't work very well. Quadratic is not much better, but a little bit. And then we've got a cubic regression. That brings our r² to about 0.9569, so not too shabby. Let's see if we can do better with a quartic regression. And that brings us up to 0.9876, which is a much better fit. So we're going to go with that. So let me write down that formula. There is what we came up with for our graph. There is our crazy formula. And if you don't believe me, we can double check. These are all the same numbers. But what are we going to do with this formula to figure out the value at 2015? Well, 2015 really means we have a table value of 15. So we essentially need to do y of 15. So in order to make this happen in Desmos efficiently, I'm going to press this little button here, which exports a snapshot of my equation down to the next line. So I've just copied all this stuff down here. And to make it easier to plug things in, normally they write this by default as y equals. I'm going to write f of x. And I've basically named my function with something that I can plug into. Then I'll go down to the next level and I'll write in f of 15. And we see that that comes to about 205.507. So we can round this off to 206 if we round up. So this is going to be approximately 206 bald eagle nests. So that's it for this one. What can I say? Time flies when you're having functions. Till next time, Mr. Sutton signing off.